British Columbia is a forest province. More than 50% of the dollars generated in the provincial economy are derived from the forest industries, which supply world markets with a wide variety of forest products. Out of a total of 134 million acres of productive forest land, the British Columbia Forest Service, representing the provincial government, has administrative control of all but 7 million acres. Primary consideration used to be given to forest management, but it is now apparent that more consideration must be given to other uses of forest land. A primary resource user must now plan his activities to enhance or complement other resource values, such as recreation. British Columbia possesses one of the fastest population growth rates in the world. Population has increased from 1.8 million to 2.35 million in the last 10 years, and is presently increasing at the rate of 2.9% per annum. As the population grows, the land base available for the production of forest products diminishes, a condition we share, or will soon share, with other forested areas throughout the world. The increased population pressures will inevitably lead to some reallocation of the land base, accompanied by an increased demand for forest products. Faced with these facts, the Deputy Minister of Forests established the Forest Productivity Committee in 1970 to provide guidelines and leadership in the intensification of forest management practices in British Columbia. The committee began by investigating the methods used in other countries to increase forest productivity. Conceptually, the forests in British Columbia can be considered in three layers: the old-growth mature stands, of which there are approximately 40 years' supply still to harvest; second-growth immature stands, which have been naturally regenerated; and recently established plantations. Although the old-growth mature stands will supply our needs for some time to come, it is apparent that the areas where increases in productivity are most likely to occur are in the second-growth immature stands. But the problem is, which treatment regime should we use to increase productivity? And what are the costs in relation to the benefits? With the advent of computers, sophisticated techniques are now available which make large-scale productivity studies possible. The problem analysis convinced the committee that modeling and simulation techniques could ultimately provide the required solutions. However, the first prerequisite was a data bank. The immediate objective, the preparation of managed stand yield tables to include an evaluation of specific treatments in terms of growth and monies invested. The program which was developed calls for data to be assembled on all relevant parameters, including soil and climate. At the same time, it was decided to adopt the metric system, and also to classify all projects using the Universal Transverse Mercator Grid, as it was apparent that Canada was moving towards the adoption of a universal grid reference and the implementation of the metric system. To date, we have been primarily concerned with the growth and yield of mature stands. Now, we must become concerned with the growth and yield of second-growth stands. The problems are which treatments to use and what techniques to use to evaluate the tree growth of the different species. In anticipation of the ongoing requirements, a three-tiered level of mapping has been introduced. The first level stratifies a region into productivity zones. This will ultimately improve yield calculation. The second level, an extensive resource inventory, will, together with the forest inventory, provide the data needed for the preparation of working plans. The third level is an intensification, which provides specific information on problem areas. A methods trial was initiated in 1971 to test the feasibility of the initial proposal. The results were sufficiently encouraging that a working plan was developed. Homogeneous stands of pure Douglas fir and western hemlock are selected as test sites and different treatment regimes applied. A series of 9 treatments covering different levels of thinning and fertilization, both singly and in combination, are replicated twice. Treatment response is evaluated in terms of growth, with particular emphasis on soil and climate, and also in terms of capital invested. As regards the amount of data required, it was decided that the minimum number of plots for coastal British Columbia was 500 1/20th hectare plots. The flowcharts show the different phases of the program, commencing with the initial selection of the areas. Permanent reserves are then placed on the sites. Once this has been done, the crews go in to establish the plots. Photographs are then taken using 70mm fixed base aerial photography. Climate stations are established and the data compiled, at which time the treatments are allocated at random. The computer printouts aid in selecting the trees to be marked. The data are recompiled to ensure that the thinning criteria have been met. Plots are fertilized at the optimum period as indicated from an analysis of local weather conditions. Fertilizing and thinning are carried out in the fall. Finally, an initial measurement is made in the dormant season, and a second series of 70mm fixed base aerial photographs obtained. The reconnaissance phase commences with an examination of the appropriate aerial photographs. Candidate areas are selected on the photographs. In 1972, 102 candidate areas were selected, of which 17 were finally approved. Although the initial screening provides valuable indications, all areas must be subsequently inspected on the ground and a permanent reserve placed on the area before establishment. To qualify, a candidate area must possess a homogeneous soil. A pedologist conducts a soil reconnaissance and digs mini soil pits to determine whether the area is acceptable. If the candidate area is accepted, detailed soil sampling is carried out. Duplicate soil samples are obtained from each installation. In the laboratory, the samples are described and analyzed. A full range of chemical, moisture, and bulk density measurements are obtained. All trees on the candidate areas are examined for root rot and other diseases or defects. The ground vegetation is examined and classified as an additional means of ensuring homogeneity. A 50-meter grid map is made and ribbons placed on appropriate trees to identify the plot centers. The work of establishing the plots now commences. First, the center of each plot is located and a center post marked and set in position. The center post is then used to locate the plot corners. Square plots are used to facilitate the preparation of stem maps for modeling and simulation. The plot is then divided into quadrants to ensure the necessary quality control. Outside the perimeter of the plot, a buffer zone is established. This receives the same treatment as the plot to eliminate edge effect. A permanent diameter breast height line is established at 1.3 meters above germination point. Diameter measurement lines are only established for trees within the plot. All trees over 5 centimeters diameter breast height within the plot are tagged with permanent, numbered plastic markers. Temporary paper tags are used in the buffer zone. Tree heights are measured to provide a check on the heights derived from the 70 millimeter fixed base aerial photography. Lean and sweep are also recorded. Increment cores are obtained from each of the designated sample trees. The increment cores are packaged and prepared for analysis. The growth patterns of individual trees and forest stands are influenced by climatic variations. Increment cores provide an insight into the effect of such variation, and analyses are being conducted to determine the effects of climatic cycles and to develop predictive equations. This is important in terms of planning capital investment in treatment regimes. Different analytical techniques are employed, including the ADO-X tree ring counting device, soft X-ray techniques, and densitometers. Following plot establishment, the areas are photographed using 70 millimeter fixed base aerial techniques. The photographs are examined using a wild A40 or Zeiss topocard, at which time a series of crown measurements are obtained. The photographs are also used to obtain the height of every tree within the plot. By combining the data from the field with that obtained from the photographs, a complete record is obtained for each individual tree and stem maps prepared for each plot. Treatment response depends on an understanding of the soil, an appreciation of the climate, and hence a climate network is an integral part of the program. Each installation has its own individual climate station. The climate network has different levels of instrumentation. At the lower level, a certain number of base parameters are measured. The highest level, or benchmark station, is capable of measuring solar radiation, net radiation, soil temperature, and soil moisture. When the data have been assembled, a climate zone map will be prepared to provide a better understanding of treatment response. The amount of moisture prior to, during, and immediately following fertilizer application is critical. Fertilizer is generally applied during the fall in coastal forests. To date, 3 rates of application have been used: 225 kilograms per hectare, 450 kilograms per hectare, and 675 kilograms per hectare. An additional level of 900 kilograms per hectare will be added in 1973. Prilled urea, 46% N, regular grade, is the fertilizer used. The dates of each application are plotted on the precipitation charts. In addition to understanding the effect of fertilization on tree growth, it is essential to understand what happens to the fertilizer. To this end, work is being carried out on the impact of urea fertilizer on nutrient leaching. Tension lysimeters have been installed, and work is now in progress on a variety of typical forest soils. This should result in a better understanding of what happens following fertilizer application in terms of its effect on the ecosystem. Trees are marked for thinning following plot establishment. The computer printouts are invaluable in selecting trees to be cut. The printout gives species, diameter breast height, location, basal area, tree class, crown class, pathological condition, and other data for each tree. It also indicates the basal area to be removed. 2 thinning regimes are employed. 1, the removal of 20% of the basal area. The other, the removal of 35% of the basal area. A further level will be added in 1973, which will remove 50% of the basal area. The thinning data are then processed to ensure they meet the specifications as to the percent of basal area removed and D to D ratio. Certain trees are selected for intensive study in connection with volume table and variable density studies. To date, 261 Douglas fir have been felled and measured. 5 discs are removed from the bole at 30 centimeters, 1.3 meters, the first complete live whorl, base of the complete needle complement, and halfway between this point and the tip of the tree. These are analyzed for bark and wood volume, taper, bole shape, and other factors relating to crown development. The stumps of the cut trees are treated with borax to prevent the spread of fomes annosus. Harvesting to close utilization standards could seriously deplete the nutrient capital of certain sites, particularly at high elevations in coastal British Columbia. This could lead to a loss in productivity. Studies began on sensitive subalpine sites in 1972 with the cutting of samples of western hemlock and western red cedar. Weight, volume, and length are measured. Samples of wood, bark, branches and foliage were taken from 10 points on the bole and 3 points in the crown to obtain detailed information on biomass, volume, and chemical content. The remaining trees on the site were measured for diameter breast height, total height, and crown length. In all, some 850 samples were ground and weighed for chemical analysis by flame photometer, and the results cross-checked by auto-analyzer. Returning to the core program, as winter approaches, the test sites are reflown. Both color and black and white pictures are obtained. These are used to confirm crown measurements, height, and the coordinates of the trees following treatment. On the ground, crews make the initial measurement. The measurements made during plot establishment are not used to determine treatment response, since they were made during the growing season. They do, however, provide the basis for allocating treatments and checking the accuracy of the initial measurement. The Managed Stand Yield Table program, now in its second field season, is projected for completion within 10 years. In 1972, 210 plots were established, and to date a further 280 plots have been located for establishment in 1973. Reconnaissance is still proceeding, and by the end of 1973, the 500 plot core will have been established. However, locating areas has proved extremely difficult, and a new experimental design will be required in 1974 to extend the program. Work on this has already commenced. As regards the economics of stand treatment, a task force has been established to identify, collect, and analyze the costs associated with intensive management, and to select the criteria to evaluate alternative treatment regimes. One of the first tasks has been to standardize terminology and costing. A new approach has been developed and is presently being tested by both government and industry. Different conditions and treatments are being sampled. Starting with the identification of the problem, the first task has been the creation of a data bank. And now that a comprehensive review of modeling and simulation has been completed, models are being developed to predict tree growth, to rank treatment alternatives, and to optimize resource allocation. These will ultimately be combined into a resource allocation and impact simulator, which will, hopefully increase yields, improve forest management practices, and minimize resource conflicts. But first, we must understand what we want to do, why we want to do it, what effect it is going to have on the total resource, and how much it is going to cost.